Awesome. My name is Mohammad and I'm from Drexel University. And my today's talk is about a thermodynamic-based framework for production of porous lightweight aggregate from waste coal combustion ash. First, I'm going to go over the introduction and motivation of doing this study. Then I'm going to talk about the concept of synthetic lightweight aggregate. Then I'll talk about development of a thermodynamics-based framework. Then I'll present some of the results for production of bottom ash-based lightweight aggregate. And then I'm going to wrap up this presentation with the summary. So we know that every year something about 100 million tons of coal combustion ash is produced. And you can see the breakdown of them over here. And we have different recycling rates for each of them. But what we know is, in general, something about 60% of them are recycled and the rest is moved to the landfills. And some of them are causing problems to the environment. And an example of that is Kingston fossil plant spill that happened in 2008 and caused damage to groundwater and rivers around it. The other problem that we're aware of is that lightweight aggregate is kind of expensive and there is limited accessibility to them in the United States. If you take a look at the map on the right-hand side, you can see that we have the lightweight aggregate manufacturers, and the distance to concrete producers kind of adds up to the final price of the lightweight aggregate and makes it more expensive. So the solution that we're proposing here is, what if we convert the unused or waste coal combustion ash in the landfills to lightweight aggregate? And by doing so, we're going to increase the local accessibility of the lightweight aggregate. Therefore, we can reduce the final price of lightweight aggregate. We're going to be able to prevent natural resource consumption, and that's because the typical lightweight aggregates in the market are clay, slate, and shale-based lightweight aggregates, which are natural resources. And finally, we're going to be able to promote landfill diversion. So basically, the lightweight aggregate manufacturing process that we had for producing them in our lab was first blending. So we have a suitable particle size for our lightweight aggregate for raw material. Then we did pelletization, and in this step, we used the fluxing agent, which in this case was NaOH solution or sodium hydroxide solution. And fluxing agent, to be clear, is a component or chemical agent that reduces the melting temperature of synthetic lightweight aggregate. So we're going to be able to save energy in that sense. And the next step was drying the material. In this case, we did that at 40 Celsius degree and 30% RH. And finally, we sintered the material at furnace or a kiln at 1160 Celsius degrees. We used two types of bottom ash over here, low calcium, high calcium. For the low calcium, the calcium content was about 3%. For the other one, something about 22%. You can take a look at the spherical type of lightweight aggregates that we produced from bottom ash here. So the concept behind that is we want to form the fresh pellets before sintering and sinter them at a temperature greater than 1100, in our case, 1160. And basically what we expect to get is a porous material where we have partial melting in the material, a combination of liquid and solid phase. So the formation of that liquid phase will help us to entrap any gaseous phases produced during sintering and create the pores for us. And if we're successful doing so, we can make sure we have a bloating mechanism occur in the lightweight aggregate, and we have a porous or lightweight aggregate. So going over literature, we know that there are three conditions that needs to be satisfied to have successful production of lightweight aggregate or bloating mechanism. First of all, we need to have formation of liquid phase in the lightweight aggregate. Second, as I said, we have a solid and liquid phase at the same time in the material, and we need to have appropriate viscosity for that, because viscosity can limit the deformation of lightweight aggregate and maintain the spherical shape of the lightweight aggregate. And of course, it can control the pore size in the material. And finally, we need to make sure we have some gas release by the material to be able to form the pores in the lightweight aggregate. Having these three harmonized, we're going to have bloating mechanism occurred in the lightweight aggregate. So how do we quantify these parameters? For liquid phase formation, we use thermodynamics modeling to quantify the liquid phase formed in a material. To estimate the viscosity of the solid liquid phase, we use Browning model and Krieger model that I'm gonna go into detail in the next few slides. And for gas release measurement, we use thermogravimetric analysis. So as I said, for thermodynamic modeling, we're going to use fact state software, which is based on Gibbs free energy minimization algorithm. And for that, we're going to use the chemical composition of the ash plus fluxing agent as the inputs of the model. And we're going to run the model under normal condition. And the temperature that we were interested in was 800 to 1400 Celsius to take a look at the most stable phases in that range during sintering. For viscosity, as I said, we're going to have a combination of liquid phase and solid phase. So for liquid phase, we use empirical model of Browning, which is heavily relied on the chemical composition of liquid phase, which is depicted by A factor over here. And the way we quantify that is by getting the chemical composition of liquid phase, which is an output of thermodynamic modeling. For solid phase, we use Krieger-Doherty model. Basically, it accounts for the volume fraction of solid in system and how the packing works, and gives us a final estimation of the solid liquid phase in the system. For thermogravimetric analysis, was used to quantify the gas release in the material in the lightweight aggregate. We use the TGA that we have in our lab. So basically, we create the fresh pellets. We crush them using mortar and pestle. We pass them through sieve 200. We repeat the process to make sure we get a good representative of the sample. And then we basically simulate the sintering by going from room temperature to 1160, staying there for 4 minutes. So taking a look at the results that we have over here, we have a phase diagram of a low calcium lightweight aggregate plus 10% NaOH. And on the right-hand side, we have the example for high calcium. Basically, you can see the most stable phases, the predictions for lightweight aggregate. And what we're really interested in is the slag or liquid phase content in the material, which is depicted by the red graph over here. So we can go over the graph and say, for instance, at 1160, which is our temperature of interest, how much liquid phase formed in the material, for instance, here 59%, and in the case of high calcium, about 65%. So we did the same procedure for 0%, 4%, up to 16% sodium hydroxide in the system. And one observation that we kind of predicted was that as we increase the NaOH concentration in the system, we're going to get more liquid phase. And that's because NaOH is a fluxing agent, and that was predictable for us. So we also took a look at the porous structure of the material using X-ray computed tomography. For instance, we have here the low calcium with 4% NaOH, and below that, we're going to be able to see low calcium with 10% NaOH. So one observation here was that for 10%, we kind of observed formation of spherical type of pores, if I can get my pen over here. So spherical type of pores over here, but we didn't observe the same type of pores for 4% lightweight aggregate. We did the same X-ray computed tomography for high calcium. You can see the 4% and 10%. Below that, the observation was those type of pores was formed in both of the 4% and 10% for high calcium here. So correlating this observation with the liquid phase content, it suggests that if we have more than 50% liquid phase in the material, in the lightweight aggregate, we can make sure that type of pores which help with the bloating mechanism is going to occur in the system. That's why we suggest 50% as the minimum amount of liquid phase required for pore formation. We took a look at the viscosity of the lightweight aggregates. On the left-hand side, we have the low calcium predictions, and on the right-hand side, we have the results for high calcium. One observation was as we increase the NaOH concentration, the viscosity of solid liquid phase decreased in the system. And the reason was NaOH acts as a fluxing agent, so we're going to get more liquid phase, and we expect to reduce the viscosity. And the second one was that NaOH acts as a network breaker in the liquid phase system, so it decreases the viscosity. The other observation for high calcium was that for high calcium 10%, the viscosity stayed above 100 pascal second, but for 16%, it fell below 100 pascal second. And we correlated that with the 3D reconstruction of our material. And as you can see, for 10%, the spherical shape was preserved. On the other hand, for high calcium bottom ash with 16% NaOH, the shape was changed to elliptical shape. And finally, we took a look at the thermogravimetric results to estimate the gas release potential from the material, a typical graph of that over here. On the x-axis, we have the temperature. On the y-axis, the mass. The black dashed line shows the mass change over increasing temperature, and the red graph is the derivative of that black line, where each peak shows the decompositions happen during sintering. What we were really interested in was the gas release at temperatures close to sintering, because that's where we believe liquid phase is going to form, and that gaseous phase is going to be captured. The minimum amount of gas release that we captured was for low calcium bottom ash lightweight aggregate with 16% NaOH, which was about 0.12%. And when we correlated that with the X-ray observations, that was the suggestion was that the gas-filled pores were still formed, and it says that that minimum amount of gas release, 0.12% of the lightweight aggregate mass, could still create those big bubbles in the lightweight aggregate for us. Putting these three together, we were able to have a graph over here. On the x-axis, we're going to have the liquid phase content. On the y-axis, we're going to have the viscosity of the material, and each of those points is correlated, is showing one of our aggregates. And the color shows the gas release potential for the lightweight aggregate. So as we suggested, the liquid phase, the minimum amount of liquid phase should be 50% to ensure pore creation in the system. To ensure we have a spherical shape, we need to have 100 pascal second viscosity, and our study shows that 10 to 6 could be an upper bound below which we can ensure pore expansion is going to occur, and above that, the force encapturing one of the pores is too much to allow for pore expansion. And we observed that 0.12% gas release could be enough to make sure that gas-filled pores are going to be created in the system. And by putting these three together, we are able to propose a working zone where if the lightweight aggregate is placed in that zone, we can make sure bloating is happened for that lightweight aggregate. So if I want to wrap up this talk, what we observed was we need three concurrent conditions to occur so we can make sure bloating is going to happen, formation of sufficient amount of liquid phase, appropriate viscosity for solid liquid phase, and enough gas release for the material to make sure pore creation is going to occur. So for liquid phase, the minimum amount was 50%. For viscosity, the range that we suggest is 100 pascal second and 10 to 6. And the minimum gas release that we observed was something about 0.12% that ensured pore creation is going to happen in the system. So I just need to thank my collaborators, Ratin Rao, Dr. Garboksi, Dr. Spatari, Dr. Sohan, Dr. Farnam, Dr. Bilan, and I should thank NSF for supporting this presentation, this research. Thank you all. I would be happy to take if there is any question.
Thank you very much, Mohammad.